In section 4.8, we're going to be looking at applications, word problems that involve trigonometry. A lot of these will go back to what you've seen in your prior classes, and then we're going to get into a few that are a bit more complicated. Couple concepts that we need to be familiar with is the idea of angle of elevation and angle of depression. Angle of elevation is all about if you were the person standing at that location, how much would you have to look up? What angle would you need to look up in order to see whatever object they're discussing? Angle of depression is similar, except for this time it's comparing to straight horizontal, just like here. Straight horizontal from your eyesight, how much would you need to look down? Okay, and sometimes you have to be theoretical and assume you could put your eye on a ground or eye on some sort of object and then look up and down from that exact location. So again, it's all compared to horizontal, how much you have to look up versus look down for elevation and depression. Okay, just something we want to be aware of as we look at this. So the first one is an angle of elevation problem. We're looking at a situation, it says the angle of elevation from the buoy to the top of the Barnea, I don't know exactly how you say that, Bay lighthouse, 130 feet above the surface of the water is 5 degrees. What is the distance x from the base of the lighthouse to the buoy? So we have this buoy out in the water. And so here's our water. It's a really rough day, apparently. And there's a lighthouse in the distance. We're told that from the buoy to the lighthouse, 1 is the distance we want to find. So that's actually the base here. The horizontal distance between the buoy and the actual lighthouse is the distance we're looking to find. We want to know, and what we're told is that if we look up from the buoy to the top of the lighthouse, we would have to look up at an angle of 5 degrees. If that's the case, and we know the height of this lighthouse is 130 feet, because we're told that the top of the lighthouse is 130 feet above the surface of the water. So the question is, how far away is this lighthouse? So we have a nice little right triangle here. We know with the angle that we're given, we know the opposite side. We want to find the adjacent side, so hopefully we know which trig function that is. Why don't you pause this and set up the trig function that you think you should use? Okay, hopefully you have this set up. It is a tangent function. So tangent of 5 degrees is equal to opposite 130 over adjacent, unknown. Okay, we solve this. The variable we want in the denominator, we might think about it as simplifying by clearing fractions or by cross multiplying. Remember, tangent of 5 over 1. And so if I tend to look at it as cross multiplying, so I get 130 equals x tangent of 5. And then we divide by the tangent of 5, and our x value, our distance, is 130 divided by the tangent of 5 degrees. I really don't want to get a decimal approximation until I absolutely am at the end of a problem so that I'm not using rounded values to calculate along the way. Okay, now we're going to go ahead and put this into our calculator. So we've got, first of all, we are typing in a tangent of an angle, so we need to make sure we're in the right mode. If we check our mode, I'm in radians currently, so I need to change to degrees because the angle that I'm entering in is in degrees. Okay, then we can go ahead and enter 130 divided by the tangent of 5. And so, checking units, we're talking about feet for the height, so this is in feet. I have 1,485.9 feet for the distance from the buoy to the lighthouse. And nothing unusual. You would have seen this exact same problem in geometry prior to this. Okay, we're going to continue on. This one gets a little bit more complicated as there's a few different triangles involved. So here we have, from the top of the 120-foot tall Talman Hall, a man observed a car moving towards the building. If the angle of depression of the car changes from 25 degrees to 45 degrees during the period of observation, how far does the car travel? So here we're standing on top of a tower, and we're looking at this car that's in the distance. So here's the road. Here's my car. Very fancy. Okay. There's my car. Originally, here's straight horizontal. Determining an angle of depression would be looking from straight horizontal downwards. So originally, I see this car at an angle of depression of 25 degrees. Okay, the car moves. And at the end of this time period, it's now in a new location. Here's the car now. Very fancy car again. And here's my line of sight to that car. The angle of depression for this car, for the same car, is now at, I draw it out here, 45 degrees. I had to look down further because the cars move closer to the building. And what we want to know is this: what is X? How far has this car traveled? We have a couple choices in this. Okay, we can create this kind of pretend triangle in the sky, which might make it easier to do because these angles that we're given are floating in the sky from straight horizontal. Or we can recalculate their angles into the triangles that are actually drawn in our picture, the triangle created with the building and the ground. I'm finding that most people like to kind of stick with the angles that are given. So I'm going to go ahead and have these floating triangles. Okay, hopefully we can recognize that the distance in the sky is the same as the distance on the ground. So here's my new X that I'm trying to find. All right, so we have two triangles. We don't know any side besides the fact that we do have one piece. We have the fact that this is 120 feet tall for this building. So this triangle over here has 120 feet for a length and 120 feet for a length here. And so we can figure out some side lengths for the triangle. Now what we're trying to find is not actually a side length of a triangle, but hopefully we recognize to find this distance. If we find the larger triangles, adjacent side, since these are our known angles, and the smaller triangles, adjacent side, I think you can imagine what to do with those, but hopefully you're thinking subtract. So we need to find the adjacent side for each of these two triangles. So we'll start with the larger triangle. Okay, its opposite side is 120. We want to know the adjacent side, so again, we're doing a tangent just like the prior problem. So as I do that, we're going to have tangent of, now the larger triangle has an angle of 25 degrees. And the opposite side's 120, and the adjacent is what we want to know. Okay, again, we cross multiply and solve. So I get X tangent of 25 degrees equals 120. Dividing by the tangent of 25, so I need to take 120 divided by tangent of 125. Tangent, there you go. We get X to be 257.34. We'll go a little bit more accurate here, especially since we're going to have to do another calculations with it. So that's the adjacent side for the larger triangle. Now let's do the adjacent side for the smaller triangle. This time we have the tangent of 45 degrees equals 120 over some unknown side. Again, we cross multiply. And then we're going to divide. We're going to divide by a tangent of 45 degrees this time to get exactly 120. Had we thought for a moment, that would make sense. And so to find my distance, unfortunately I used X a few times in here, this distance that we want to find is the difference between these two adjacent sides. So if I subtract them, 257.34 minus 120, I get 137.34 feet. The car's traveled around 137 feet. Okay, I'm going to stop the video here and then we'll finish it with our next video.